Okay, so we're going to look a bit at applications of forces, modeling with statics. So that is to say, we're looking at situations where an object is not moving, it's static, it's in equilibrium, but there might be various interesting things going on in terms of the structure of the system. So we could have strings, things threaded on strings, things connected by strings, strings going over pulleys, things sitting on an inclined plane rather than on flat ground, a force being applied, some sort of mystery force, and effectively whatever is involved in this system, the object is not moving, so it's all balancing out. And that's what we're talking about when we're talking about modeling with statics. And I think initially it's going to be a little bit of a refresher, but then once we get into some examples, I think it'll be sort of halfway stuff you know, but halfway a little bit new. Okay, so let's look first at something which should be more of a refresher, but let's just quickly remind ourselves. That is how to split a force into components using an angle. So this is going to become, especially in year 13, this is going to become second nature to you. It'll become so obvious that you won't really have to think about it so much, I hope at least, with enough practice. So whenever you're seeing a vector and you're considering an axis, to split it into two components, that is to say for a 2D vector, you're just going to automatically think, right, if I know the angle, by default calling it theta, and I know the magnitude of the force, let's say, it's just capital F, that's some number, then you should be very comfortable with just being able to sort of rattle off that this component here, the adjacent to the angle, that's F cos theta, and this one here is F sine theta. Because you're going to be, especially in this topic, but also this chapter, and well, eventually in the wider world, when you're thinking about how you split up forces, you're always going to split it up in the 2D case in terms of a cos theta and a sine theta component. Okay, so you should be very comfortable with that. And if it's something where it takes you time to think about which one's cos, which one's sine, you just want to make it second nature. So you just need to remind yourself the mystery side, which is touching the theta, that's the cos one, and the mystery side, which is not touching theta in any way at all, that's the sine one. Okay, so I mean, there's obviously a full justification for why that's the case, but you want it to become second nature. Whenever you see an angle in a triangle, right-angled triangle specifically, you want to be able to say that component's the cos, that component's the sine. Okay, so that's that little reminder there. The next thing then is a reminder of how tension works in a string, but then also to just address a very specific case. So the title here that I've given is on an object threaded on a string. So just to clarify what I'm talking about here, let's say you've got a string. Okay, so I've just got sort of a string. It's connected between 2 points. Okay, so I've got a yellow string, and if I attach, let's just say I attach a ball to it, I don't know, I super glue it somehow, then this we would just say, I mean, this is just an object or a particle attached to a string. Okay, it's not threaded. By threaded, what we mean is that this object, whatever it may be, is technically able to freely move on the string. So for example, if you picture, let's say I took a ring, like a ring that you'd wear on your finger, and I threaded the string through the ring, and picture the real life scenario, that ring, I mean, it may or may not move, but it has the ability to, right? So if I took this ring in my hand, I could physically move it along the string. And perhaps, if there wasn't much friction, what you might find in reality is that the ring would eventually settle in the middle. Because it's threaded, it's got freedom to move. Gravity pulls it towards the middle and it ends up there. Okay. Now that may depend on friction, which is something we'll come to later. But the key thing is here, when we're talking about objects being threaded on a string, they technically have the freedom to move. Okay, it doesn't mean they are moving, but it means they do have the ability to. Okay, and that's the difference between something that's just attached to a string. Okay, so with all that said, let's look at an example of an object threaded on a string and consider the forces that are going on in order for this equilibrium to be maintained. Okay, so let's just break down what we're being told here. We've got a smooth bead, so that's this black dot here, threaded on a light inextensible string. So the string is effectively this part here, this solid black line going down and then the solid black line going up here. Okay, and it's all one single string. It's not two strings, it's one string. And this black object, this bead, technically has freedom to move anywhere along that string. Okay, the string obviously has the same length at all times, and the bead has the freedom to move along it. Okay, but when it's talking about a bead, it's the same thing really as a ring, same as the previous example. Okay, the ends of the string are attached here to X and Z. And let's also just mention here, the string is light, meaning it has no mass, or we model it as having no mass. And it's inextensible, which means we know the string is always the same length. It's not like an elastic band. Okay, and these two fixed points X and Z are on the same horizontal level. Okay, that's fine. That's what we've got in the picture. And the bead is then held in equilibrium by some horizontal force, some mystery force. We have no idea where it's coming from. You know, it could be like a rocket booster, or it could be something more realistic like the wind or something, but it doesn't really matter. But for some reason, this bead has got a force of 8 newtons and it's pushing it. This force is being applied and pushing it to the left. Okay, or at least that's where the force is directed. But the bead is in equilibrium, right? It's not actually moving. And then we're also told that this angle here that the string makes with the horizontal is 30 degrees. Okay. And it's going to ask us to find the tension in the string and the weight of the bead. Right. So first off, let's just consider for a moment this diagram and make sure it in some way kind of makes sense, right? So you remember before I was saying, well, if you put a bead on a string, you might typically expect it to end up in the middle. So if I just quickly draw that up, you might expect, you know, something where you've got the string kind of like that, and the bead is, you know, this ring or this bead is sort of just sitting in the middle there. That's what you might expect if you just hung a string between 2 points at the same height and dangled the bead on it, right? But the point is then this force comes along, this 8 newtons, and it's effectively pushing this bead over to the left. So it looks less like what I've drawn there, and it looks more like you know, something like this, for example, right? So this bead is being pushed over to the left. The length of the string is the same, but it might look a bit more like this, right? The bead's being pushed. And in this specific case, it just so happens, coincidentally, and for the sake of making the question easy, that the string becomes vertical, right, with this precise force of 8 newtons, right? Now, I mean, that's quite special, right? There's no reason it would end up vertical. It just so happens that the forces are balanced in such a way that this part of the string becomes vertical, okay? But obviously, if this was 8.1 newtons, it would go beyond vertical, or if it was 7.9 newtons, it would go and it would end up having the bead being a bit further to the right instead. Okay, cool. So the diagram makes sense. What are we trying to find? The tension in the string and the weight of the bead. Okay. Oh, there was one thing then I didn't quite mention. Let me just go back for a moment to my diagram here, which was the tension on the string. Right, I spoke about the definition of threaded. I didn't actually speak about the tension. So when this bead is on the string, the tension works as follows. Hopefully you remember that, you know, the tension throughout the string is the same. So that means the string if you imagine this ring here is actually, you know, it's not really floating in air, is it? It's almost, let me draw a more accurate picture, because really you're not going to have the string being curved like that, are you? In the real world, you'll end up with the string being a bit more like this, right, with straight components, and the ring is then going to just be dangling off the end of it, right, and sort of pulling it down. And what you'll then have is a tension force, which is the string sort of pulling the bead that way, or the ring that way, and the same force pulling it that way as well, so they kind of cancel out. And that same force also, it happens to be the same here, where it's attached to the wall or whatever it is that it's attached to, and likewise here. Okay, and we could call all of these you know, T. Okay, they are all the same value, same tension. So that's a key thing here. When an object is threaded, same as when it's attached, the tension is being applied on both sides of the object, and it's the same amount, and it acts in the direction of the string itself. It acts along the line of the string. Okay, so let's go back to this diagram and let's see how we can solve this question. So probably the first thing we can do is let's draw the tension and the weight, actually. So let's label a few extra forces. So there's going to be tension pulling the bead upwards along that bit of the string, and the same amount of tension, same magnitude, different direction, pulling it that way. The bead also has a weight which hasn't been labelled, so let's put the weight in as well. And that weight is, what are we told what that is? We're not told what it is, so let's just call it W. Okay, so perhaps it's not going to actually affect the final answer. Let's then resolve forces horizontally and vertically. Now, conveniently, all of the forces, almost all, are either vertical or horizontal. The only one that isn't is this tension force. Okay, so that tension force, let me just draw these a bit bigger actually. Okay, there we go. So just giving myself a bit more space. That tension force going up diagonally, what angle is it to the horizontal? It's also just 30 degrees, isn't it? And we know that from just geometry. When this line here crosses these two parallel lines, the corresponding angles here are going to be the same. So that's 30 degrees. And what we know then is that, from what we spoke before, the adjacent side, that's t cos 30, and the opposite side, that's t sine 30. Okay, so we can just break it into those components. And now we can resolve all of the forces horizontally and vertically, and we can set them to, we know that they'll add up to 0, right? And we know that because the bead is in equilibrium. Okay, so let's see, horizontally, what have we got? We've got t cos 30 going to the right, and we've got the 8 newtons going to the left, and we know that in total that equals 0. Okay, and then upwards, resolving vertically, you can do up, you can do down, it's up to you, as you know. We've got t going up, we've got t sine 30 going up, and we've got w going down. So let's do that. T plus t sine 30 and minus w, and that's equal to 0. Okay, so now what we've essentially got here, we've got two equations with two unknowns. So it's just simultaneous equations, isn't it, to solve. Cos 30 sine 30, hopefully we know those off by heart. Cos 30 root 3 over 2. And for our second line, sine 30 is just a half. Okay, so let's see then, working with that that one we're looking at now, we've got 3 over 2t equals w. effectively. Or, yeah, no, that makes sense. 3 over t equals w. And then let's also look at this top one. We can find t from this, can't we? Because we've got root 3 over 2t equals 8. So therefore, just doing the rearranging in my head a bit, if that's successful, we've got 16 over root 3 for t, which we could equivalently write as, it's up to you, 16 over 3 times root 3, if we don't want a third on the denominator. Okay, so that's our t. And then from where we were just a moment ago down here, I'm going to say therefore the weight is equal to we've got that 3 over 2 times t, and t is here, we just worked it out. So what's 3 over 2 times this? That's going to be 16 over 2 root 3, or in other words 8 root 3. So that I just got from substituting our t value here into this equation. Okay, and that gives us our two values there. That's the weight, and that is the tension in the string. Great, let's look at one last example and then you can have a go yourselves. So in this example, we've got inclined planes and pulleys and some sort of mystery force. So let's see what's going on here. A mass of 3 kilograms rests on the surface of a smooth plane, which is inclined at an angle of 45 degrees to the horizontal. So that's this one. That's the 3 kilogram one. Let's just make a note of that one there. So that's 3 kilograms. Okay, what's next? The mass is attached to a cable which passes up the plane along the line of greatest slope. In other words, it's just going up the slope. And passes over a smooth pulley. That white circle, there's the pulley at the top of the plane. The cable carries a mass of 1 kilogram freely suspended at the other end. So that must be that one. That's freely suspended. It's off the ground, and that one's 1 kilogram. Let's make a note of that. Okay. The masses are modelled as particles and the cable as a light, inextensible string. Okay, so in other words, you can use your usual simplified assumptions, which we always do. The cable or string doesn't stretch and it has no mass. There is a force of P newtons, that's that one there, acting horizontally on the 3 kilogram mass, and the system is in equilibrium. Okay, so nothing is moving. Does that make sense that nothing is moving? So just think about it intuitively for a moment. So we've got this heavy ball on a slope. Normally if I had a heavy ball on a slope, it would start rolling down. But this 1 kilogram object is sort of pulling it up a little bit because of the pulley. But you'd expect, of course, well, it's still going to go down, isn't it? Because 3 kilograms is heavier than 1 kilogram. It's going to roll anyway, you'd think. It kind of depends on the slope. But intuitively, it seems a bit funny that it would still not go down. But then you've got this helpful force P, which is pushing this object to the right, which in some senses, a component of that P is helping that 3 kilogram mass get pushed back up again. So it's counteracting the downward forces. And the value of P is such that it just happens to all balance out. Okay, that's what's going on here. Cool, so there's only going to be one specific value of P, which makes this ball balance perfectly. If it's a little bit less, the ball will roll down. If it's a little bit more, the ball will actually be pushed upwards. So we need to find the P that makes it stay in equilibrium. Right, so for all of these, I mean, you've got part A, B, C. Find the magnitude of the P. Find the normal reaction of this 3 kilogram mass and the plane. But all of that, to be honest, it will all come naturally out of doing the one single task, which is to resolve forces horizontally and vertically. In this case, I suppose not quite horizontally and vertically. You want to resolve the forces along this rotated axis that I think we've spoken about before. So you've actually really got a rotated axis that you're thinking about, which represents the line of the slope, So that yellow line that I'm marking out there should match the direction of the slope, and then this other line, which is perpendicular, is just the perpendicular line to the slope. Okay, so that's what we're going to consider as our two directions when we resolve forces. Right, so let's draw the diagram in a little bit more detail now, because we need to label some forces and their components. Okay, so I just started drawing the slope there. I'm going to just add in this string going over a pulley. I always find that a little bit tricky to draw, actually. Okay, there, just about managed it. What else have we got? 45 degrees here. Okay, that's 45 degrees according to the horizontal. Right, so let's start labeling some forces. The obvious one is P. Now, I actually don't quite like the way they've labeled it on the diagram. It's a bit nasty, because really it's more helpful to label the force in such a way that if you're using arrowheads, the arrow is pointing out from the object, whereas this kind of looks a bit like an arrow is pointing into the object. I suppose that's more to just indicate that this mystery force is somehow, acting from the left. So, for example, someone could be, I don't know, blowing on the ball, or applying some sort of force at a distance from here. Maybe there's a magnet that's over here and it's causing this magnetic ball to have a force pushing it to the right. But on our force diagram, let's just use the normal arrows, and I'm going to have P sort of like this. Okay, so let's do it up here. That's P. Okay, and it's acting to the right from the ball. What else have we got? We've got the weight, and we know how much that is. The weight force is its mass times g, so that's 3g. And what else do we have? We've got the normal reaction, which is perpendicular to the surface of the slope. We don't know what that is yet, but we'll just call it R. Okay, anything missing? Just think for a sec. Are there any more forces acting on this object? You've also got the tension along the string. Okay, so speaking of tension then, let's also label the same tension for this other object now. That will also be here as T. And that second object also has a weight of 1 times g, so just little g. Okay, that's an actual number though, not an unknown. Okay, this should hopefully then be enough for us to resolve forces, set everything equal to 0, and come up with a solution. So just think for a moment, which of these forces on the diagram are not currently aligned with either of these two axes, specifically for this object, let's say. So let's resolve forces for this object here. The R, that is along that line, that's fine. The tension, that's along this yellow line, that's fine. The 3G and the P, however, are not aligned with either of these two axes. So we're going to split those up. Let's split up the 3G first. How are we going to do that? So if I do a right angle triangle, okay, there's my right angle triangle. I've split the 3G up into two components now that are, in fact, along these two axes. What are the components? Well, it depends what the angle is. What's this angle here? Now, you'll get used to this, but you should be able to figure out that that angle must be 45 degrees. In fact, exactly the same as the angle of the inclined plane. And remember, this is always going to happen. Whenever you've got an object on an inclined plane, by geometry, whatever that angle is there will be the same as this angle here when you split up the weight into its two components. Okay, it'll always be the same angle. So if this 45 was 20, this would also be 20. Okay, so then this here is 3G cos 45, and this part here is 3G sine 45. Okay, and then what about P? So P gets a bit messy. I'm just going to use blue just so you can distinguish it a bit. P I'm going to split according to that triangle. Hopefully you can see it. And I'm just going to sort of direct it, some lines just to show what I'm referring to. What are the relevant angles? Well, the angle here, if I just sort of colour that in, that blue angle there, that's going to be 45 degrees, right? It's just going to line up perfectly with this angle because we've got what is effectively the horizontal P and then the line of the string, which is the same as the line of the slope. So that's 45 degrees there. So I'm not going to write in the 45 degrees because it's too messy, but that there is 45 degrees. So therefore we've got here P cos 45, and over here we've got P sine 45. Okay, and that one's acting into the surface of the inclined plane. Okay. Right, this is why you've always got to draw a big diagram. Unfortunately, I didn't quite give myself enough space. So now let's resolve the forces. The force is going, let's say, up the plane. Okay, what are they? So what have we got going up the plane? We've got, okay, the tension's going up. Let's write that, so that's T. What else have we got? The component of P going up is the blue one here, the P cos 45. That's also going up. Oh, P cos 45. Anything else? The weight has a component going down, which is this one here. That's the 3g sine 45. So minus 3g sine 45. And I think that's it. So we're going to equate it to 0 because it's an equilibrium. Okay. The r is completely perpendicular to the direction of the slope, so it has absolutely no effect. Okay, and then let's consider the direction going up and out of the slope, so the perpendicular line to the slope. We've definitely got r going up. T is irrelevant. We've got a component of P going into the plane. That's the P sine 45. Let's take that away. And we've got 3g with a weight also going into the plane. That's 3g cos 45. And we're going to equate all that to 0. Okay, great. One thing I've missed, a key bit of information, which is pretty obvious. What is the value of t? We actually know it straight away, not by considering that object, but by considering this one. Remember, this ball's not moving, neither is this ball, nothing's moving. So this object here can't be moving, and it's only got two forces acting on it. You've got the tension going up and g going down. So T must be equal to G. Straight away, we can get that. So let's make a big note of that. T is equal to G. So in fact then, wherever T appears here, wherever T appears in any of these equations, I'm just going to replace it with G, which it was in fact, unfortunately, just that one place. So we've got G there. Okay, but that's one unknown removed. Right. Okay, what I'm going to do now is just give myself some space. Let's get rid of the diagram. And now we're just going to work with the maths. So we've got our resolving forces equations, and we just need to solve these. So sine 45 and cos 45, we hopefully realise are actually the same value. It's the one of the few times when sine and cos have the same output, and it's 1 over root 2. So let's write that out. G plus p over root 2 minus 3g over root 2 equals 0. R minus p over root 2 minus 3g over root 2 equals 0. Okay, now really at this stage you could probably solve this yourself. You've got two equations, two unknowns. So you can feel free to give it a go if you want to. Otherwise, I'll just quickly finish this off if I can. So I'm going to call that equation 1, that equation 2. If I add the two equations together, so add together both sides of both of them, this and this will cancel. These will just double up, and I'll have a g and a plus r. So we'll have g plus r minus 6g over root 2 equals 0. So this is my nice little shortcut, and that implies r must be equal to 6g over root 2 minus g. And what's that equal to on the calculator? It's 31.777878, so yeah, something along those lines. So let's say about 7.8. I think the final answer in the book says 32. Okay, so that's our value for r. Nicely done. So we've actually answered part B first, doesn't matter. And then part A, the magnitude of P. So we can pick, well, P actually we can get immediately from the first equation. So let's take the first equation multiplied by root 2. It's a bit of a funny notation I've written there. I'm not doing 1 times root 2. I'm just doing this equation times root 2. And I get root 2g plus p minus 3g equals 0. That implies p must be equal to 3g minus root 2g. Or in other words, 3 minus root 2 times g. What's that equal to on the calculator? 3 minus root 2 times 9.8. Right, I get 15.54. Just had to move this a bit because I've cut off the answer slightly. 15.54, that's the answer for the magnitude. Okay, so we've done both A and B. The way we did it was simply to resolve forces in two perpendicular directions, up the slope and perpendicular to the slope, equate them to 0 because it's in equilibrium, and solve the equations. Okay, so really these kinds of questions are all about first setting up the equations of the forces correctly, and then part 2 is just solving them. It's the setup that's probably the part that's going to be a bit more new and a bit more about where you mainly want to focus your practice. Okay, and then part C is quite a basic question. It should make a lot of sense to you, really. How do we use the assumption that the pulley is smooth in our calculations? So the pulley being smooth is a necessary assumption if we want to assume that the tension throughout the string is consistent. So we've got the same tension throughout the whole string. So for example, if I just go back to this image here, if it was not a smooth string, I could not assume that this T and this T and this T and this T are the same. Okay, because it's a smooth string, I can. So that would be the sort of one sentence that you would need to write for that kind of question. A smooth pulley allows me to assume that the tension is the same throughout the whole string. Or you could perhaps say the tension is the same for both parts of the string on either side of the pulley. Both of those sentences are perfectly acceptable. Okay, cool. All right, so let's take a look at some questions now. I think I've got 3 for you to have a look at. 3 questions. Here is the first one. Okay, so you've got an object, it's hanging, it's threaded on the string, and you've got this interesting scenario. We've got 2 different angles of the string, and that's mainly because there's a force pushing the object a bit to the left. Okay, part C, so easy. I've just given it to you just about 30 seconds ago. So this is mainly about part A and B. But obviously you should be able to answer C. So give that a go, and when you're ready, pause the video now. Okay, let's take a look at the answers. There we go. Oh, for part C, maybe I have to go back on what I said a moment ago. Perhaps I didn't read the question correctly myself. Let me take a quick look. Ah, fair enough. I misled you slightly a moment ago, or at least before I prepared you for the question. Yeah, because of course there's no pulley. Sorry, I was thinking of a pulley scenario. If it's a string and a pulley, then assuming that the pulley is smooth tells you tension is the same throughout string. If you're assuming an object threaded on the string, if that object, the bead, if that thing is smooth, it just means it doesn't have any friction. I mean, they're sort of both within the same realm of, you know, they're sort of the same sort of scenarios being explained here. There's no friction, or the forces are consistent. It's the same kind of thing. But I suppose it is an important distinction to be made. So check carefully, unlike I just did a moment ago, what are the objects that it's actually talking about. Here it's talking about the bead on the string, not a pulley on the string. Okay, because of course there's no pulley in this question. Cool, all right, so there's your full answer for part 5. Let's look at the next question. Okay, so just skipping ahead a bit in terms of difficulty, have a look at this one. Remember, when you're told tan theta equals 3/4, you should be able to very quickly, just directly from that, get cos theta and sine theta. Okay, if you need to remember how to do that, just try drawing a triangle. Draw a triangle where one of the sides is 3 and one of the sides is 4, and you've got an angle theta, and you've drawn it in such a way that clearly tan theta, that's opposite over adjacent, gives you 3/4. Then work out the third side, and you'll be able to get fractions for sine theta and cos theta as well. Okay, double check your work. You can just do tan inverse of 3/4, and then do sine of that, and then do cos of that, and you'll get sine theta, cos theta. Okay, so just my brief hint for that question, immediately looking at it. I mean, perhaps you'll need it, perhaps you won't, but you should, in theory, be able to get perfect fractions for those two there, sine theta, cos theta. Okay, cool. All right, and then my other little hint there is make sure you draw a big diagram, because there's lots of forces going on here. There's friction, there's normal reaction, there's tension, there's weight, and you want to find the components of these. So you need a big diagram. If you draw a small diagram, you're just going to get a bit annoyed with yourself, probably, trying to figure out what you're writing there, and it'll look a bit ugly, which isn't nice. Cool. Give that a go. Pause the video now. Okay, and there are your answers for that one. Okay, and final question. So we've got an object, it's on an inclined plane, so there's going to be weight, there's normal reaction, and then you've also got two sort of mystery forces, or at least one of them is known, it's 5 newtons, and the other one is 5 newtons. Okay, so these could be 2 strings, it could be, you know, 2 rocket thrusters, it could be 2 anything, we don't know. But they are just 2 forces being applied. Okay, here, let me just have a quick read through it, actually double check. No, that should be fine. You are just resolving forces as usual. I assume the 8 marks comes from the fact that you've got 2 external forces rather than the usual 1. But I suppose in a sense, one of them is sometimes the tension. Anyway, have a go at that question. Try and resolve the forces, draw a big diagram, and when you think you've got the answer for P, you can take a look. Pause the video now. Okay, and there we go. That is apparently the answer, 0.40 newtons.